Well, hello and good evening, minions. Uh, my name, as always, is Nathan, and hello, Jesus of Cakes. I am so happy to see ya. Yeah, I have been away for a while. It's been a while since I streamed, and I apologize very much for that. Um, yeah, no, it's been a busy several weeks that I haven't had energy or brain space to be streaming. But yeah, I have missed doing it. I've been looking forward to when I've got some time and brain power to do it. Um, yeah, because last couple weeks. Oh gosh, I've been spending a lot of time in the lab, which has been a nice change actually. It's been a while since I went into the lab to do like some experimental work. Um, but yeah, so my professor and I have been working on getting this last paper of the PhD out, and so we've identified like a few spots where we need to get some more experimental data. Some of it is just like retaking old data that just we found out now like it isn't quite good enough to um, it doesn't have the precision that we would like it to have, and we think we can do better. So we're going to reacquire some stuff. But it all takes a lot of time and effort to remake certain compounds and then run them on our instruments. But yeah, so that's what I've been working on for a while there, and also so he hired me a few months ago to help him with some other projects, some collaborators who are sending him some samples that we need to do some electrochemistry on or crystallography and stuff. Um, and we're supposed to be getting some of those samples soon. So we got to get some of our instruments running that have been kind of ignored for a couple years because because I haven't been responsible for upkeeping the lab. So it's been kind of the stuff has been sitting idle for a while, and some of it wasn't working too good. So we've been doing a lot of maintenance and cleaning and stuff like that. Yeah, and then last week, yeah, I mean I don't know if I'd call it stressful. Like it's been a fair bit of work, but nothing's like, oh my god, we need to start doing stuff now. No, it's been just like, yeah, we'll fix it, as soon as we can manage. But yeah, we're often limited by we've got some parts on order from vendors. Usually vendors are in the States for a lot of the stuff we need. Some of them are overseas. But yeah, so a lot of it has just been waiting for parts to come in. Like there's a couple parts for our glove box, and because we keep an inert atmosphere in a big box and do some of our more sensitive chemistry in there. But it took us a while to track down the problem too. But like one of the valves was leaking a lot of nitrogen, so we're just going through way more nitrogen gas than we should be, and it gets expensive. It all adds up. So we finally tracked the problem down, and so now we've got valves on order from the States. And it's 2 day shipping, 2 days. So it was supposed to be here like a week and a half ago, and it's still not. So yeah, nice little express shipping. It's great. It's probably just being held up at the border. That is commonly the problem, um, but yeah, so I've been doing a lot of stuff in the lab, and then last weekend, some of my very very good friends got married, and I was the one who I was officiating the ceremony. So that was a lot of prep work there, but it was very very fun. We all had a great time. Um, but yeah, between all those things, I have been busy as heck. and, um, yeah, and I'm still kind of busy as heck, but now I've got a little bit of time, and so I figured I would come back here and do some chemistry with you because I missed doing this and it's been fun, and I really hope that you've been doing really well too. Jesus and cakes. Your school year should be done. Hey, did you have to write any exams for the end of the school year? Or? Yeah, so let me know how you've been doing. Oh, yeah. Oh, yeah. And in the meantime, I'm going to just pop over to the worksheet over here and go over what I did last time, which was a while ago. So yeah, I just started working through. This is just a practice exam that I pulled from online, and so we were talking about. So this is looking at the approximate pKa values for. Oh, let's zoom in so you can actually see it. Approximate pKa values for a couple different protons on this structure, and pKa values are corresponding to. It's basically like saying how acidic is this hydrogen, or like how easy is it to pull this hydrogen off of the molecule that it's attached to. So you have been doing summer school, so you can get your AA stuff and stuff when I finish high school. Been trying to get around on the Chaplain bill in Florida, which was real bad. So fun stuff. Got a bunch of books made you happy camper. Oh, that's awesome. So yeah, so summer school. What kind of courses are you taking for summer school? And what is a chaplain bill? I am not familiar with this. But yeah, books are always great. Most of my book consumption lately has been in audiobooks. So I take the cats and the dog out every morning. Just out to the yard to play and explore, and I usually pop an audiobook on when I'm there, and then when I'm working at the lab, I usually have audiobook going there too. I'm almost halfway through the Lord of the Rings at the moment because Spotify got that on for free as read by Andy Serkis, and it's fabulous, and he does all sorts of funny voices, and it's great. All right. Made a challenge with a friend that you'd finish 2 AP classes in a summer, so those in Spanish, honors, pre-calc honors, art, and college algebra. Holy cow, that's a lot. God, I thought I was busy. But no, that sounds awesome. Wow. Yeah, pre-calc will definitely serve you well in like almost any kind of degree after, because I remember when I started university, I had taken zero calculus in high school. I had absolutely none. I didn't know what it was, and then I got into my first physics course. And he started talking about, oh yeah, just take the derivative of this of like the speed, and you get the acceleration. And I had to lean over to my friend and like, what's a derivative? And thankfully I had a really lovely study group who taught me the basics that I needed to know to get through the course. And yeah, so it was it was a bit rough having no experience in calculus before that, but so yeah, good on you for getting a bit of a grounding in it now. Chapman Bill was HP 931, replace school counselors with religious volunteers. Oh. Oh. Well, that's awful. Yeah. Hello, Tian. Um, yeah, worst mistake you ever made was taking AP Physics. Yeah. No, I feel you. I'm right there with you. Like it's pretty rough trying to get through this stuff that uses calculus when you don't know what the hell it is. Um, yeah, yeah. Ugh, yeah. No, I sympathize. Like I'm in Alberta, which is a province that is currently run by a government who is very hostile to education in a way that sound a little similar, perhaps less extreme than Florida. Um, but yeah, it makes me very upset very frequently to see governments just railroading these awful bills that are just really contrary to the concepts of education. Makes me big mad. Um, yeah, yeah, that really sucks. But we'll get through it. There are I'm certain that there are a lot of educators who will like do their very best to try to subvert those kinds of directives without breaking them and exposing themselves to prosecution or getting fired. But yeah. Yeah, no, you're absolutely right about that. Like an uneducated population is a submissive one. That's absolutely correct. Like education is like one of the most powerful tools that we have in order to just to be a progressive, open, welcoming, kind society. Education is the cornerstone of all of that, and it is absolutely a hallmark of conservative governments to underfund any kind of public education or to direct it into some kind of religious or ideological stream, and specifically to cultivate that kind of a submissive population. So yeah, I think you're bang on. And I've said for years that the conservative governments will cut funding to education in order to keep people dumb enough to keep voting conservative, and that unfortunately has played out in front of our eyes in far too many places. Um, yeah, yeah, it's a little rough out there sometimes, but that's part of why I like doing stuff like this, so that we can just like talk. Well, first of all, like talk about these things and call it what it is, but also like to contribute in some small way to just having an educated society, because that's just objectively, um, that's that. Yeah. Hey, yeah, it's me. Um, yeah. Oof. All right. All right. So now that we're all just a little hot under the collar, I'm going to talk about some chemistry. So yeah, last day we were talking. Which I think it was like weeks ago, but that's fine. So yeah, pKa values are talking about the acidity of a proton, which is essentially just like a measure of like how difficult is it for a base to come along and pull a hydrogen off of its molecule. And so we were looking at hydrogen A or proton A. Those like hydrogen and proton are effectively interchangeable terms when we're talking about hydrogen that's part of a molecule. Those terms are used interchangeably. So hydrogen A is attached to a nitrogen, and because the nitrogen is more electronegative, it pulls electron density away from hydrogen. It makes it easier for a base to come in and pull the hydrogen off, and so that makes it a little bit more acidic than hydrogen that's attached to a carbon. And the approximate pKa's are about 35 for the hydrogen attached to nitrogen and 44 for the hydrogen attached to a carbon. Now, I would like to point out that I don't think that anybody should take time to like memorize what the pKa's of certain hydrogens are like hydrogen on an amine versus hydrogen on a carbon. Um, don't like pull up pKa tables and just try to memorize a list of different pKa's. That's what we have tables for. The memorization doesn't add anything to it doesn't make you a better chemist to have pKa values memorized. As long as you can like look up a pKa table and look at what the pKa values are. I've known professors who will like have this on exams, and I think it's diabolical. I think it's terrible because the memorization doesn't describe how good of a student or how good of a chemist someone is. Um, like I was able to kind of piece together partially by process of elimination what the approximate pKa's of these were. But that's because I've been studying this stuff for 12 years, and while I have taken very little time to try and memorize pKa values, it absorbs over time, and that's what memorization of these things should be. Is like I've used pKa tables enough times, I've answered enough questions that involved it, that I kind of know approximately what the pKa values will be. I think that's the way to go about this. So unfortunately, not everybody agrees with me, but well, it's okay for people to be wrong too. That's fine. Um, yeah. Then we talked about condensed formulas. I'm not going to go over this one too much. So this was just like if you go through these carbon groups one by one. Now, did I? Okay, so yeah, so I wrote down kind of a couple of examples of how you take a structure and convert it into a condensed formula. Like, so condensed formulas, they have structural information encoded into them. And so with these, we just kind of go over it and just like go through them left to right and compare them to the so compare them to the molecule that you're given. So this one started with this CH3 is a methyl group, and this specifies 3 of them, which doesn't track with what the molecule is. This has a methyl group here and a methyl group here. And now it does have 3 methyl groups over here, but this condensed formula has a 3 methyl groups on both ends, so it can't be that one. This is wrong. This is not descriptive of what the molecule is. And so between CH3 and so what's the difference between CH3 and CH3? That is an excellent question. So like here, that's pretty big. Let's make it small. Okay, or the number on the CH2. Okay, perfect. We'll go through that. So in this one, in B, it's got CH3 just all on its own. And that specifies a methyl group. Like that would specify one of these guys. I'm going to actually erase these so that I can talk about it a little easier. Okay. So this CH3 could track to that, and that's totally fine. But when we start getting into the bracketed CH3s, you'll always find the bracket with a subscript next to it. And is it like multiple ones of the methyl groups? Yes, it is exactly that. So you use the brackets when you have multiple of a group. So like this CH3 is just like a group of atoms, and so this specifies that there are 2 CH3s here, so it's specifying this one and this one, so it refers to both. But yeah, that's exactly it. So you bracket the CH3 if it is like if there's multiple of them that you need to specify. There is another way that you can that you would use the brackets, and that is if we're talking about inorganic compounds. So compounds where you've got a metal, and let's say we've got an oxygen and okay, so let's call it this. So you got a metal in the center, and you've got 3 hydrogens attached to it, and you've got an OH, a hydroxyl group. So when you're making the formula, these would usually be in square brackets for metal complexes. So you would say OH, and you would put parentheses around the OH because the group that is attached to the metal is an OH. And then you would say, well, actually, let's change one of these. So we'll make this CH3. CH3, and H2. Okay, so when we're talking about metal complexes, where we've got a central metal atom that is connected to very possibly a bunch of different groups, then we start to bracket things even when there's no multiples of them, but just because this is telling us that there is an OH group that is connected to the metal, and there is a CH3 group that is also connected to the metal, and there is 2 hydrogens connected to the metal. Now, this H2, I have not put parentheses around. And so that is going to indicate that there are 2 H's, two hydrogens attached to the metal center. Because if I did bracket put the H2 in parentheses, that would mean that this H2 is one group. And so that would indicate that it's not 2 hydrogens. It would indicate that it is a molecule of hydrogen. So an H2 molecule on the metal. So then if there were no brackets, would it mean that all 3 are connected to each other and the metal atom? If there were no brackets, if there were no brackets, this would be a mess. I just need to try and think for just a moment what this would even look like. No, it's a brackets parenthesis. I know what you're talking about. It's all good. I am also using them kind of interchangeably and wrong. It's a whole thing. So yeah, if there were no brackets, then you would have. So here's a good example of how this would go. So let's just say there is this. A metal connected to S and 4 oxygens. Whoops. If there were no brackets or parentheses or whatever you want to call them, this is kind of the structure you would assume. I haven't drawn in lone pairs or any kind of multiple bonds or anything. This is just kind of the basic skeleton of what you might expect. But when you put parentheses around, then what you'd expect is a metal connected to a molecule of sulfate, SO4, um, which okay, so this has the bond going to sulfur. It would actually be through one of the oxygens because sulfates, little units of SO4, can coordinate to metals. They do so through an oxygen, not the sulfur, but that's fine. But putting the brackets around it is important because if there were no brackets at all, then it gets really weird. Like you have to, if it's more than one atom that is connected to the metal, just put brackets around it, because it keeps things orderly and specific, instead of just being weird, funky chaos. Yeah. So yeah, that's kind of the other situation where you would use parentheses to set off these different groups. And actually, there's one more. Okay, all right. So there's one other situation where you would use brackets. So if we were to go CH3 CO CH3. So it's like chemistry grammar where the absence of parentheses represents a real complex structure. Yes to both of those. Like it is part of chemistry grammar, which is why, like, if we took something like this formula, if we took out all of the parentheses here, I would look at that and I'm like, that's gibberish. That's just it's just a bunch of letters strung together with no real meaning. So the parentheses are part of the grammar of chemistry, and also the parentheses set off these things that have this complex structure, and just like breaks it into these pieces, and you know that those go together. So yeah, definitely yes to both of those ideas. Okay, so for this formula, you could do so yeah, it's not immediately clear if this oxygen is part of the carbon chain, like this, which describes an ether. Because an ether functional group is just an oxygen that is like inside of a carbon chain. But that's not what this molecule is, because this carbon must have 2 hydrogens on it in order to have its full octet. So that would be a clue that this is wrong. But in order, just for clarity and to keep things easy, what you'll often see is you'll have like a carbon and then an oxygen in parentheses. And what that is indicating is that, let's draw out all the atoms. So what the parentheses indicate is that this carbon is part of a carbonyl functional group. So it's a carbon double bonded to an oxygen. So often in cases like these are called ketones. Often in ketones, you'll see an oxygen in parentheses next to the carbon it's attached to, and that's an easy way to say that this is what's going on. A chemist with a reasonable amount of experience would be able to work without the parentheses, but it just kind of makes it easier, just to like kind of flag to the chemist that, hey, there's a break in the carbon chain. This is kind of beside the carbon chain, not within it like an ether. Yeah, so those are all the situations that offhand I can think of where you'd use parentheses in a formula. Yeah, and then it's just a matter of following this along and going through each group in order, and just making sure it matches. Then we went through calculating the formal charge on the oxygen. Oh, you bet. I got you. And so that's the formal charge is just equal to the valency minus the number of electrons around it. And in formal charge, we count the electrons by breaking each bond in half, giving one electron to each atom on either end of the bond. And when we calculate it like that, we find that a oxygen with 3 bonds and 1 lone pair comes out with a formal charge of +1. And I know we've gone over that before, so I'm not going to go over that really any more than that, but I'm going to start answering some other questions. But of course, if you have any other questions, any topics you want to talk about, I always prioritize that and would be very happy to. Because this, after all, is tutoring, and tutoring always adjusts itself to what the student wants or needs to go over. Okay, so the HCH bond angle in methane is closest to one of these. The Lewis structure of methane is just like this. So the Lewis structure is very much simplified, but it looks from that as if it should be a 90-degree angle, but of course this is only a two-dimensional representation of the molecule, and the molecules are not two-dimensional. Wonder about thorium if we're going bismuth 213, something through the power plant process. I think though, right? So I'll go chapter 10. It said no in Google had mixed sources. Ooh, that is a great question. Let me think about that for just a minute. I think that is this is something that we will look up. But yeah, I'm just going to finish my thought with this first, and then we're going to get onto that. So methane is a tetrahedral molecule. Come here, need my model kit. Okay, so molecule methane, CH4. It is not flat, and it looks much more like this. Any kind of model kit is going to have these kinds of things. This is a tetrahedron, or the shape of it is tetrahedral, if you like, and it is the shape that it is because of like the one overarching rule of chemistry. Like I've said a million times, and I'm going to say it a million more times. 98% of chemistry is just trying to reduce electron-electron repulsion as much as possible. And tetrahedra, like this, are more efficient at spreading out the electrons than a flat, like planar molecule like this, right? Because these angles are, I can write, sure I can, 90 degrees. So in a two-dimensional molecule, the angle between these four, when they're as spread out as they can be, is 90 degrees. But in a tetrahedron, which is the actual shape of methane, the angle between hydrogens is larger than 90 degrees. So we've got our dash bond, and we've got our wedge bond. And remember, the dash means that bond is going away from you. Like if you're pointing at the screen or the paper or whatever, the dash bond is going that way. and the wedge bond is coming out of the plane of the screen towards you. And that's very much like this. So let's see if we can set this up in a way that's actually sensible. So it should be like that-ish. So we've got these two, and I haven't actually drawn these angles exactly right, but so you'll have two of these hydrogens will be in the plane of the surface you're drawing on. One of these will be coming out towards you, and one of these will be going away from you. And when you arrange it like that, these angles are 109.5 degrees in like a completely ideal molecule, which methane is very close to this 109.5 degree angle between the bonds. And again, this is because those bonds are just the kind of where the electrons are localized that are being shared between these two atoms. So like between the carbon and the hydrogen, this bond is where the electrons are localized. It's just at the closest approach between the carbon and the hydrogen. And so when you have these two bonds being 109.5 degrees away from each other, they are further away from each other than when the bonds are 90 degrees from each other. And so this is, again, just spreading out the electrons a little bit more and lowering that electron-electron repulsion. 109.5 degrees is the ideal because math, basically. It's the maximum angle that you can get between four different bonds arranged around one center. And so there's lots of different molecules. Like you could put silicon in the middle there and have methyl groups around there. So you have this is a molecule called tetramethylsilane. And it's a very important molecule for us because it's one of our primary NMR standards that we use. And these would also be approximately 109.5 degrees. Want to get closer to the next hydrogen, make it less? No, it won't. This 109.5 degrees is as far away as these hydrogens can be. So, like these, how can I explain it differently? I want to get closer to the next hydrogen. It's important to remember that this 109.5 degrees, this is the angle between all of these hydrogens. So between this hydrogen and this hydrogen is 109.5 degrees. Between this one and this one is 109.5 degrees. Between this one and this one is 109.5 degrees. So yeah, exactly. It's not a 360 degree. We're not confined to the 360 degrees of a circle, right? Because this is not a two-dimensional shape. In a two-dimensional shape like a circle, then which is exactly what this is depicting. Then if you divide that into four, then yeah, you've got 90 degrees per quarter, right? Because this is essentially the same as putting them on a circle. But we're not talking about a two-dimensional shape. We're talking about a three-dimensional shape. And so when you have, like this is basically existing in a sphere. And so you've got the carbon at the center of the sphere, and then the hydrogens around it will occupy 4 points on that sphere. And in the configuration where the points that you put on the sphere are as far away from each other as possible, you get an angle between them of 109.5 degrees. So that's just how the math works out for this kind of tetrahedral shape that's kind of projected onto this spherical space. Does that make some more sense as to why it's that angle? Excellent. Awesome. Love to hear. Yeah, and like and this principle is really like how we figure out all of the kind of ideal geometries for molecules. So you'll sometimes hear about Vesper theory, which sounds like it should be VES, but it's not. VSEPR. So Vesper theory is how we kind of predict the shape of molecules based on their connectivity and how many electrons are around them and all that stuff. I'm not going to fully go over that right now, but it allows us to predict shapes like this one, and the angle between them, and it extends to like metal complexes that have more more groups attached to them. So like this one, this is called an octahedron. And so it is a central atom that is surrounded by six groups. And in this case, if you project this onto a spherical space, then these angles, the ideal angles, are 90 degrees because now you have to put 6 points on that sphere and keep them as far away from each other as possible, and that gets you to a 90 degree. That's a great question, and it's one that I didn't figure out until like fully the end of my first semester in university. So this has 6 groups around it, but it's called an octahedron because how I'm wondering. I'm just trying to think of how to draw this. Okay, so we'll go. Is this the right way to do this? Huh. It's a tricky one to draw, but I maybe if we do it like this with 4 of them in the plane and then okay, so that one's coming towards us and this one's going away from us. I think that works. Okay, so we got a central point, and then we've got 1, 2, 3, 4, 5, 6 points around it. So it's just like an octahedron. You generally only see these in metal complexes, but like let's just Nathan, come on, let's focus on the shape. Okay, so if you draw lines between each of the points, let's put the lines in a different color. So we got a line from this top point to that point that's it's on a bond that's going away from us, so that goes down there, and then onto this point, and then to that one, and then okay, so we're just going to connect all these points to each other. This isn't a very good drawing because I'm not a very good artist. But, so basically what we've made is, here, if we make it like this, oh my goodness, that's actually brilliant. Yes, 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 yes. Yes, D&D dice. I'll be right back. Okay. Okay. So I couldn't find my D&D dice, which makes me a little sad, and I'm really going to need to look for those later. But that's okay. Okay, that's almost good enough. So, yeah, it's the exact shape of a D8. Hello, how are you? You're cutie. So yeah, an octahedron is the exact shape of a D8. It has, yeah, exactly. It has 8 faces on it, eight sides. So it's a four-sided pyramid. Well, it's 2 four-sided pyramids that go butt to butt. So yeah, but if you count the points around the center, it's got 1, 2, 3, 4, 5, and 6. But that makes 8 sides out of this thing. So yes, that's exactly right. Yeah. D&D dice. My goodness, they're good for everything. Yeah. God. Just highlights how very, very good I am at drawing stuff. Yeah, it's real good. But yeah. So that's why that. Okay, now. So that deals, I think, with the angle question. We're trying to come back. Heck yeah. You should always have D&D dice on you. Because they're just great. You never know when you're going to need to roll for initiative. Not that you do that with the D8, but you know. Anyways, okay. So I want to look at thorium radioactive decay series. So it says it ends up at lead 208. That looks pretty nice. Okay, so thorium, if it can make bismuth 213. Okay, so thorium. So we start at thorium 232, which I also want to Okay, so thorium-232 is the main naturally occurring isotope of thorium with an abundance of 99.98. So that's an extremely high abundance isotope of it. No, that's not actually a digression. That's a really important point, because we do need to consider what is what is the isotope of the fuel, in this case thorium, that is useful for doing fission. So it's like with uranium. Uranium is mostly, I think, about 95%. I could be wrong on that. But uranium is mostly uranium-238, which is somewhat radioactive. It like has a half-life in the billions of years. But what is used for fuel in fission reactors is enriched uranium, which has a reasonably high percentage of uranium-235, because uranium-235 is more radioactive than uranium-238. So it is in fact very relevant to figure out which isotope of thorium is used in the molten salt reactors. Might be 232 since it's fertile, and they add plutonium. Oh heck, I don't know the isotope for that either. But yeah. So, yeah, uranium-232 can capture a neutron to form thorium-233. 2 beta decays to uranium-232, which is fissile. When used in the thorium fuel cycle in nuclear reactors for prototypes. Blah, 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 blah. Okay. Okay, so, the other thing I keep doing that. Okay. So one thing I want to look at is what are the known isotopes of thorium. Let's see how this is. Yeah, so we got natural abundance over here. So yeah, the only other significant isotope is thorium-230. And it's got, so the half-life of this one is about 75,000 years. So a vastly more radioactive isotope than thorium-232, which is, like 14 billion years. So I'd suggest that we should look at decay series for 232, 230, I think 229, possibly. Do more radioactive materials have shorter half-lives? Yes. Yeah, no, that's basically how that goes. Because like if you think about, like, if you've got a gram of like thorium-232 that lasts 14 billion years, its half-life is 14 billion years. So in 14 billion years, 0.5 grams of that thorium will have decayed. Because they emit electrons, right? So emitting electrons is one type of radioactive decay. Absorbing them also is, absorbing particles in itself is not radioactive decay, but it can lead to radioactive decay. It's usually neutron absorption that does this, because radioactivity is all about the stability of the nucleus itself. And so if you capture an electron, it's being captured into the valence shell. So it's not the nucleus that gains that electron. So gaining an electron would probably not really lead to any radioactive decay. But electrons can be produced by radioactive decay, because neutrons can break down into protons and electrons. And there's a bunch of fancy particles, physics-y stuff that you can do with radioactive decay. But yeah, it's usually like either like if you have something, well, actually, like they were saying in so thorium-232 is a material where it can capture a neutron to form thorium-233, which means that the nucleus of uranium-232 gains a neutron. And by doing that, we get to thorium-233, which has a half-life of 21 minutes, which is which is extremely radioactive, like very, very, very highly radioactive. So by changing the number of neutrons in the nucleus, you vastly disrupt the stability of that nucleus. Yeah, it's a massive difference. And this is how kind of like nuclear chemistry goes, is that the stability of a nucleus, especially when we get to really massive ones like uranium and thorium. A small change in the makeup of the nucleus can vastly affect the stability. Because think about it, like there's majorly two forces that are happening in a nucleus. There is the nuclear strong force, which is like the attractive force between nuclides, which is nuclides being either neutrons or protons. And so the nuclear strong force is an extremely strong force. It is like almost unthinkably strong. But the thing about nuclear strong force is it only operates at extremely short distances. And when I say extremely short, I mean like not the entire width of a large nucleus like uranium or thorium, which are like big clumps of neutrons and protons. So the nuclear strong force acts to hold together like little small local domains of the nucleus. But you also have the electromagnetic force that is operating in a nucleus, because protons have a positive charge. And so in the electromagnetic force, you've got positive charges repelling other positive charges, and we're packing all these positive charges into a tiny space, which is really it causes massive repulsion. Like, chemistry is based on reducing electron repulsion, which is the same thing basically, but at thousands of times the distance as like protons are from each other. So it causes it to rip away like magnets. Yes, exactly. So like you have all these protons, all these positive charges that are being crammed in together, but they want to repel each other. And if you get a big enough nucleus where the nuclear strong force isn't acting over the entire nucleus, so like parts of the nucleus over here are like they're not pulling on a part of a nucleus over here via the strong force. Like the force doesn't cross all that distance. So like they're all being held to the next nuclides next to them, but they're not being held to the ones on the other side of the nucleus. So that force drops off very, very quickly, even across the nucleus. But the electromagnetic force operates at a much larger range. And so all the protons on this side of the nucleus are repelling all the protons on this side of the nucleus. And the ones that are closer together are repelling each other more, and a lot more. And so when you have really large nuclei like this, then you get these explosive forces of the electromagnetic force. It's this massive repulsion. So I put a huge clump of protons to increase the possibility of getting the unprotected part of a nuclei. Kind of like that. Like, so the protons are kind of like spread throughout this nuclear soup, because you got protons and you got neutrons, and as much as possible, you'll have like the protons kind of evenly distributed throughout the nucleus. But at some point, the electromagnetic repulsion overcomes the strong force, the nuclear strong forces. So also, how come there's weak spots on it? It's like shallow water on a pan where there's like still spots uncovered. So, I. I. It's. I don't know if that's a perfect analogy. Like, it's. I think it could be. So, like, I think that could have some relevance here. So it's like. Yeah, like the slime example, I think might be a little bit better because like yeah, you'll have certain weak spots around it, but like it's a little more homogeneous than that, in that like ideally you'll have protons kind of evenly spread out throughout this neutron soup. Or like ice cream, like little. Oh, I've got some black cherry ice cream right now. That's just it's fabulous. I love it so much. But like you have these cherries kind of evenly distributed, more or less, through the ice cream, and that's kind of what protons prefer to do. Like between the ice cream that is the neutrons between it. That's right, absolutely. Can't go wrong with cherry. It's beautiful. So think if you had this spherical bowl of ice cream, where you got cherries evenly distributed throughout it. All of those cherries are repelling the other cherries very, very, very strongly. But like the cherries are strongly glued to the ice cream around them, but they're not strongly glued to the ice cream further away from them. So like there comes a point, a certain distance from these pockets of positive charge, where the nuclear strong force becomes weaker than the electromagnetic repulsion, and that's when you get radioactive decay. That's when the nucleus tears itself apart from this electromagnetic repulsion. And like this is why nuclear fusion is so very difficult. It's because you have to take these positive charges in the nuclei between like the isotopes of hydrogen, and you have to smash them together. You have to get them close enough to each other that the nuclear strong force takes over, and it's very much a matter of just distance. So when we see nuclear bomb explode, we are actually watching it decay. Sorta, kinda. I'll address that in just a minute. So yeah, the act of like performing nuclear fusion is really, really difficult. Because you have to get these positive charged nuclei close together, like physically close enough that the nuclear strong force can bind them together, and so you have to overcome the electromagnetic repulsion, and we do this with pressure and heat, and that's all we can do. And so when we are building fusion reactors, we don't run them at extremely high pressure, because I assume technological issues with that. But we run them at extremely high heat. And this is like much, much higher heat than even our sun, like 10 times hotter than what we think the center of the sun is like. But the sun has the advantage of having this massive, massive gravity and huge, unthinkable pressure at the center of the sun. And it's the pressure that allows the fusion in the sun to operate at a lower temperature than fusion on Earth. Yeah, so we overcome our deficiency of pressure by going to extreme temperatures. Yeah. So when we see a nuclear bomb explode, like the opposite of semiconductors, I'm not exactly sure what you mean by that. Um, um, oh, oh, what a lovely little bot we've got. That's super great. So yeah, I'm not exactly sure what you mean by the opposite of semiconductors. But yeah, if you wouldn't mind clarifying, that'd be lovely. So seeing a nuclear bomb explode, what we see is not really the decay of the uranium or plutonium. I think they use plutonium mostly. So that is happening. The decay and this very, very, very rapid decay is what causes the explosion. But the explosion is basically just heat, just a lot of heat, and so this produces massive pressure waves. And so, like, if you watch like the slow motion videos of nuclear tests, you'll see like there'll be like a house, and so the first thing that'll happen is the size of this house or this wooden structure will just like go black instantly, and that's the thermal wave. So that is just like the initial burst of heat from the reaction, and that's followed by this incredible pressure wave that just obliterates whatever's in its way. But this is all caused by the extremely rapid production of heat from this nuclear reaction, from this rapid decay, from this oh, what's the word? There's a specific word for it. It's a critical something. But anyways, so it's you see this extremely rapid decay of the plutonium and uranium causes this release of energy in the form of heat, and that superheats all the material around it to an extraordinary degree, and that's what creates the explosion and all the devastation. Like it's so the radioactive decay causes the nuclear explosion, but really all you see is the explosion, if that makes sense. Okay, so the opposite of semiconductors, like instead of cooling down to function more complex, it heats up to do something. Yeah, kind of like that. Yeah, yeah, no worries. But yeah, so that's kind of what's going on when a nuclear bomb explodes. You have this chain reaction that just goes out of control. And the amount of energy released by a nuclear reaction, including by fission as well. By fusion as well as fission, is mind blowing. Because like nuclear reactions happen. Nuclear bombs are set off by maybe a few kilograms of radioactive material. Like it's not much stuff, but it is so much more energy released by this material than in conventional explosives or in fossil fuels. Like normal bombs are things that they operate by usually they're based on like the formation of things like nitrogen gas. So you have nitrogen containing compounds that when you like apply heat to it, or an electric shock or whatever sets the bomb off. When you apply this energy to this compound, it forms nitrogen gas. And so when you have a really rapid production of nitrogen gas and heat, again, like it's all about producing gas and producing heat. And that just makes these pressure waves that expand very, very fast, and like that's what explosives are. Is these things that produce these pressure waves and heat. Conventional explosives do it by forming things like nitrogen gas. Nuclear explosives do it by just producing crap tons of heat through radioactive decay. And this is also why bombs in space would not do very much at all. Because so like bombs here, like even like nuclear bombs, they heat up everything around it at such a rapid rate that it causes this wave of pressure and heat, but that is carried by the air that is already around it. And so if you put that in space, there's nothing around to kind of absorb that heat and carry it outwards. There's no medium like our atmosphere to do that. So like a nuclear bomb would get extraordinarily hot. It would like what you'd see is like the core of this bomb would basically become like plasma because it just get extraordinarily hot. But that's about all you'd see. Like the casing of the bomb and all that stuff would get superheated and blasted away. But you wouldn't. It wouldn't do a lot. Is pressure like electron repulsion, where nature in general wants to venture out? Yes, very much. Yeah, pressure is really like quite analogous to electron repulsion like that, and yeah, like you always want to get to kind of an ambient pressure. Yeah, that's absolutely it. Yeah, as you just want to spread this out as much as possible. Like any gas in a container is going to expand until it occupies the whole container in kind of a uniform density. And yeah, that's very much like electron repulsion. Like it operates by different principles, but yeah, totally. It's very analogous. Yeah. Okay. So, anyways, what we were here to do that I kind of forgot about. So you were wondering if we can use thorium to make bismuth 213. Now I want to go back to the decay series. So I wonder how close we get to that. So it looks. I also want to pull up isotopes of bismuth. Yeah, so also great resource for anytime you're doing nuclear chemistry. Just Wikipedia has a page for every element describing the known isotopes, their natural abundance, their half-life, how they decay. It's great. Like, again, never ever cite Wikipedia as a source for any kind of report that you do. But by all means, use it as a starting point, like because it's great. It's really useful. Okay, so what are we looking at? Bismuth, tooth. There's a lot of isotopes of bismuth. Holy crap. Okay. All right. Yeah. So bismuth 213 has a very, very short half-life. So what would we do if we were going through? If we're going through the thorium decay series, so this is starting from thorium 232. You can say the family of bismuth is big myth. Oh god. All right. Uh, um, you win the pun war for today. I don't think I can top that. So well done. I applaud. Um, yeah, so be proud of your puns. My agonized groans. I hope are of immense satisfaction to you. I hope so. Um, okay. Um, okay, so we're starting from thorium 232. So this is the high abundance, pretty much completely stable isotope of thorium. So alpha decays to radium through actinium, back to thorium nucleus, um, and then alpha decays to lead 212, which will beta decay to bismuth 212. Now, bismuth 212 has an even shorter half life of 7 minutes. So basically, what that's saying, if you had a gram of bismuth, then after 7 minutes with this gram of bismuth 212, then you would, like, half of it will have decayed. It is not. Huh. That's interesting. It's not actually telling us what this decays into. Is that excitation energy? Yeah, that's not. Okay, so this is actually missing information. I'm not exactly sure why. It could be a lot of reasons. But yeah, so this decays after 7 minutes is its half life. And okay, so this is saying there's two possible routes that this could decay, either by beta decay into polonium or by alpha decay into thallium. So basically, what I'm getting from this is that if you were to go down the decay series of thorium 232, and you would eventually get to bismuth 212, and then you've got a matter of a few minutes to fire to fire neutrons at this sample of bismuth 212, and if the nucleus captures those neutrons, it will form bismuth 213, which then has a half-life of 45 and a half minutes. So even bismuth 213 is not a stable isotope at all. This would be also highly radioactive, as beta minus decay and alpha decay. Which means that the beta minus decay, that could actually get considerably dangerous. Because at a half-life of 46 minutes, means that it's decaying fast. It's making a lot of these beta decay particles. Is there a way to halt a half-time, like how people freeze DNA samples? No, there is not. At least no way that I'm aware of, certainly. Just because we don't have much of anything that actually can interact with nuclei. Because even if you cool the sample down, it's almost exclusively going to be affecting the electrons around the atom. Yeah, as far as I'm aware, we don't have any way to intervene in the half-life of a nucleus. How do they use it for radiation treatment if it's 45 minutes? Okay, so they use things like this as radioactive tracers in things like CAT scans. I can't remember the full acronym for that, but something's CAT scans or PET scans, which is a PET. I know it's positron emission tomography, which would be a beta positive decay. But that's also done with things that have relatively short half-lives. and so uh, basically, you get someone to drink this stuff containing this radioactive tracer, or have it injected in their veins, and then you put them in a machine with detectors all around it. They pick up this radioactive decay, and they get structural information about like where these radioactive traces are throughout the body. So the way that they can use these things for radiation treatments. So it depends on the energy associated with the decay. So like here they've got this 250 kilo electron volts. It's just a unit of energy. Basically, like this is the amount of energy that's released when these isotopes decay. So bismuth 213 has this energy of actually 213 kilo electron volts. I don't, off the top of my head, know how much is a dangerous amount of energy released. No idea. I'd have to look that up. But essentially, they try to find things that have radiation that will be non-interactive as much as possible, and like just make it out to the detectors, or like pass through you instead of interacting with you. Which is, which I should caveat, which is not the case with things like radiation therapies for cancers, where they are trying to get these things to be destructive to tissues, but try to localize that to the cancerous tumors as much as possible. So yeah, there's a few different medical uses. They can be used as tracers that just kind of they spread throughout the body, and the radiation passes through your body without interacting with it, to get to detectors that tell doctors what's going on in the body, or they are used for things like radiation therapy for cancer, which is they try to use this radiation to destroy tumors, because some of these radioactive decays can be very destructive to tissues. So yeah, that's I know very, very little about radiation treatments in medicine, but to my understanding, which that's more or less how that goes. Do they detect tumors and such with radiation by the repulsion? No, I don't think so. I think how they would detect tumors would depend on because these tumors are usually denser than the tissues around them, I do believe, and so they will, because the tumors are more dense than the surrounding tissues, they will absorb more radiation, because there's just more stuff in the way of the radiation that can absorb it. And so that's why the tumors will often show up as like shadows, because they're absorbing the radiation instead of letting it pass through, or reflecting it or something like that. So I think it's not so much repulsion as absorption, if that makes sense. Do tumors have more melanin? I don't know. I think they can. I know skin cancers generally do, because they're they are you can have these dark spots on your skin that form what's the word, melatomas, I think is the word, and so I think the tumors can have more melanin. I don't think that's necessarily a universal thing about the tumors, but I don't know for sure. Yeah, and that's exactly like what the melanin does for us in a healthy manner is yeah, it's like darker skin is caused by higher production of melanin, which absorbs the radiation in in a way that is not destructive to our tissues. Yeah, so yeah, very much on the right track, and all of this stuff is very much interrelated. So yeah. 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 Like nuclear chemistry and radiation, I just find it fascinating. I think it's a really cool area of study, and for a while, I was really thinking about like trying to become a nuclear scientist. Um, you use my chemistry background in nuclear science, but I kind of I got a little my interest in that kind of cooled off a bit, just because I would have to have so much more solid of a physics backing in order to be useful in doing nuclear chemistry and nuclear science. So I kind of decided against going that route. Also because I wanted to get into teaching instead of that. But yeah, it's definitely like one area of science that I find endlessly fascinating. Um, yeah, yeah. All right, my friend. Well, it is coming up to almost 8:30. At least where I am. And I think I'm about done for tonight. But it has been lovely. I am very happy to be back and doing this again. Cause it's been a while, and it's and thanks for coming out and chatting. It's been lovely. Uh, and yeah. So I'm hoping to get back into this. Kind of just as much as I can handle. I think right now I'm kind of down to like a once a week kind of schedule. So for the foreseeable, I'm gonna try to like keep it to Tuesdays. Um, but thank you so much, appreciate it. And also remember the whole amygdala thing a while back. Um, I I don't think I remember what we were talking about there. Can you remind me? Because I'm very curious where this goes. You emailed the OG person who did the study on amygdala activation when people see the opposite or same race. So they haven't heard of testing for neurodivergence. Oh, right. I remember when we were talking about that. Um, that's incredible. That's really neat. I love that we just got to a question that nobody's really studied before. That's fascinating. So yeah, like first of all, good on you for just like getting in touch with this person, because it's like emailing people you don't know can be really scary. At least I think so. But yeah, people are generally like pretty excited about talking about their research and talking about these questions. So yeah, super cool. And heck, like there's a nobody's been testing for a neurodivergent, any kind of link to neurodivergency. Heck, maybe they'll do that. Maybe they'll talk about that with their colleagues and ask around. Because I feel like neurodivergence is becoming so much more part of our societal conversation. Which is great. I mean, which is how like I came to the realization that hello, I'm quite autistic. uh, which is like, over the last couple of years, like I like learned a lot about myself because of how this cultural conversation is going. And yeah, like I'm hoping that in not too long of a time frame, that like people start to really look for this, because the awareness of neurotypes is just like becoming so relevant. So I think we can reasonably anticipate more studies coming out that do talk about this. Like the difficult thing is it's hard to quantify neurodivergence, and because like there's so many different types, and so many presentations of neurotypes, and people are often not even aware. And yeah, like say like they there's so many that are not diagnosed and that are unaware. But yeah, I think it's going to keep like becoming more part of the conversation in science and in clinical trials and in psychology and psychiatry and all these things. So yeah, super cool. Yeah, thanks for bringing that up. That's neat. It's really interesting to just like come up with these questions and talk about these things that kind of like affect us, and they matter to us. So yeah, very cool. That's awesome. Thanks for bringing that up. Yeah, so I'm going to sign off for tonight. Yeah, very much appreciate you coming out and chatting for a while with me. It's been a lot of fun. And yeah, I hope I'll see you next week. And hope you have a lovely week. Okay, bye.